we said that a lot of this booklet is quite a lot of extra information that you don't really need. And I am filming this anyway, so if you didn't get a copy of the pages that are important, it's there as well. Okay. Sorry? Yeah. Okay. It's on the. You can go back and watch it on the film, but okay. So I don't want to spend too much time going through this. Okay. So we went through this as well on Friday, and we watched the video, and we said that you need to know orders of magnitude. So you do need to know sort of like the difference. You need to be able to identify different orders of magnitude. So you might be told to compare this small thing to this less small thing in terms of order of magnitude. So something might be times 10 to the 2 and something might be times 10 to the 4. You can say there's 2 orders of magnitude out. So that's the kind of question you might get asked with that. You do need to know your prefixes, so please remember those. And those are just some examples. Okay, you'll never be asked to explain just give an example of something that's 10 to the minus 15. But they might give you an example, and then you have to compare them. Okay, now these pages, you don't need to know a bit of information if you're interested in it. The history behind atoms and the elements. You probably have done it if you do chemistry already, but don't worry about it. You don't need to know that. You don't need to know the history of the periodic table. And we've already talked about atomic number, mass number when we went through the nuclear booklets. Atomic number is how many protons are in the element. Mass number is how many protons plus neutrons there are. And a nuclide is a nucleus with a specific number of protons and neutrons. So a helium nucleus contains 2 protons and 2 neutrons. Its nuclide symbol is helium-4, 2. Okay? Right. We do need to know these. So subatomic particles. So you do need to be aware of the history behind the discovery of electrons. So J.J. Thomson discovered the electron. This was the first direct evidence that atoms were not the fundamental particles of matter, because up until then we just thought they were just like basically just particles. They didn't have any constituents. They weren't made up of anything else. They were just atoms. He was awarded the Nobel Prize in recognition of the great merits of theoretical and experimental investigations on the conduction of electricity by gases. So basically, he realized that there were things smaller than the atom. So electrons was the first thing that he noticed. So that discovery marked the birth of particle physics. And in the long term, it led to the first images of the atoms using an electron microscope. And this microscope finds a beam of electrons at a target and measures how they interact with it. By measuring the reflections and shadows, an image of individual atoms can be formed. We can't actually see the atom using the light, but we can create an image of one. Okay, so all you need to know is J.J. Thomson discovered electrons, basically. You don't need to know the details of how he did it. You need to know the sort of history, the evolution of atoms and how we thought they looked. So originally we thought there was the plum pudding model, which was basically all the little particles were in this sort of a mass of pudding, okay? So basically, and they didn't have any kind of place, they just all were like anywhere really. So that was the model of the atom that incorporated the recently discovered electron, and it basically shows, if you see there electrons are just in amongst the other particles inside this atom, okay? But we now know that electrons aren't in the same place as neutrons and protons. We know that electrons are now around the outside, okay? And that's where Ernest Rutherford comes in. He's a very famous physicist. He's the one that sort of like did a lot of work with atoms and how the structure, how they're made up of. Okay, so Rutherford and sometimes Marsden, his assistant, also worked with him. He experimented with the structure of the atom itself. Okay, so he had this famous gold foil experiment, okay, where he bombarded gold foil with alpha particles, okay, and he had a detector and he detected what happened there. Okay, so he used newly discovered alpha particles to bombard a thin sheet of gold foil, or more correctly directed his students Geiger and Marsden to do so. Geiger as a Geiger counter fame. Okay. So he found that, and these are the important things that what he found. So he found that most of the alpha particles passed straight through the gold foil without deflection. This showed that the atom was mostly empty space. Okay, so basically what happened was he divided the alpha particles at the gold foil. Most of them just went straight through, so most of them were detected sort of around here. Okay. So if alpha particles could get through the gold foil, that means that the gold foil is mostly space. Okay, the atom is mostly space. And a few particles, so about 1 in 8,000, were deflected by more than 90 degrees. Some came straight back. Okay, so that showed that the alpha particles must have bounced off an object with a relatively large mass, but quite small as well, because only 1 in 8,000 bounced back. Some of them, okay, so that's when they realised they must have been bouncing back off a positively charged thing in the centre of the atom, which we now know as the nucleus because it's got protons and neutrons in it. Neutrons are neutral, so proton, it must be overall positive. Okay, so that's the important thing here. What did he find with this experiment? Okay, so that's what you need to know about that experiment. And from the results of this experiment, a model of the atom was formed with a positive nucleus and orbiting electrons. And the model is called the Rutherford model. And the relative scale of the nucleus was also established at approximately 1/10,000th the size of the atom. So right in the middle, really small, really positive. This meant that most of the atom was empty space. So there you go, there's another sort of diagram of what happened. So most of them just went through the empty space. But this one, you can see, has got deflected backwards because it's got repels from the positive. Okay, so that's what you need to know, the results of that experiment. So what you'd set up and the results. You do need to know that. Radioactive decay. We have talked about radioactive decay before with the nuclear. So spontaneous change or disintegration of an unstable atomic nucleus as it transforms itself to lose energy. Alpha particles are 4 to 2. So if you're doing an alpha particle equation, you just take the 4 off the top and the 2 off the bottom to get your Dalton product. Okay? What we did in nuclear. In beta decay, there are 2 types of beta decay. You only need to know one. We'll talk about them in a bit more detail later. So a neutron changes into a proton and an electron. Again, we talked about this in nuclear physics as well. So in this one, we've got radon. So what happens is a neutron changes into a proton. So we've got an extra proton. So we're actually adding a proton onto the bottom. But because we've lost the neutron but gained the proton, the mass number hasn't changed. So that stays the same. Plus we've got that electron, and from this couple we now know we also have an antineutrino. Okay, so we'll talk about that in a bit more detail as well. And in gamma decay, it's just energy. It doesn't change the structure. It just makes it less energetic. It's just giving out some energy. Okay. Right. Another page that you need to know. I know it's quite a lot of words, but I will summarize it and tell you what exactly you need to know about this. Okay. So the existence of quarks. Okay, so we know that Rutherford, he bombarded alpha particles at gold foil and he saw what happened afterwards. Okay, so the same kind of thing was used to discover what's inside protons and neutrons. So Rutherford was looking what's inside an atom, but then we want to look what's inside the little particles inside an atom. And we did it was a similar kind of experiment called scattering. Okay, Rutherford used alpha particles because they were the particles with the highest available energies at the time. However, over the decades, scientists would develop and improve particle accelerators, which we've done already, or atom smashers, to enable them to probe deeper and deeper into the fundamental structure of matter. As these accelerators pushed back the bounds of technology, resulting in higher and higher energy, nearly 200 particles were discovered, with exotic names like pions, muons, neutrinos. Okay, and they're quite often called the particle zoo because of the large numbers that were discovered with different qualities. Okay, so what they did was just a very similar thing to Rutherford. But he'd bombarded with quite slow-moving alpha particles. We can now accelerate things. We can move them. We can deflect them. We know that. So we can smash other particles together and see what happens. Okay, so that's basically what that's saying, is scattering is smashing particles together and seeing what happens, and observing the effects of what happens. And we realized that there are quite a lot of things inside of protons, inside of neutrons. Okay, these are the quarks. Okay, but when they first started doing these experiments, they didn't really see a pattern. But when they got more and more, when they did more and more of the experiments, they started seeing a pattern. And just like the periodic table, you know that it's now like the periodic table. At first, they were just like, I don't really know. But when they started discovering more and more elements, they started seeing patterns and putting them into sort of like a pattern. Okay, that's exactly the same thing that happened with quarks. So as with the development of the periodic table, these particles were grouped together by their properties to reveal the possibility of underlying structure. Experimental evidence to support this theory came in the 50s, when the scattering of high-energy electrons from nuclei by Hofstadter revealed some underlying patterns indicating that protons were not fundamental particles. He was a joint winner of the Nobel Prize, and this work did not conclusively identify the number and nature of the constituents of the protons, however. Okay, so he just realized that protons, they could split up into smaller particles, but he wasn't really sure what they were. And then in 1964, Murray Gell-Mann and George Zweig both independently proposed that protons and neutrons consisted of 3 parts. So basically what you can see is when you smash them together, you can see the effects of 3 different paths for each one. Okay, so if you smash a neutron and a neutron together, you can see 3 paths coming out from where the neutrons were. Okay, they're not very long-lived, so you can't really see them themselves, but you can see what happened. So we call them quarks, and the particle theory was reduced to a much more manageable number of fundamental particles. And the Standard Model, which is what this booklet is about, was developed to include these fundamental particles of matter and to describe how they interact with each other. Okay, so basically they did all these scattering experiments, and they kept doing them and throughout the years, and they realized they got more and more details throughout the years. And now we've realized that neutrons and protons contain 3 smaller particles called quarks. Okay. Antimatter. Do you need to know a little bit about antimatter as well? So antimatter is basically matter, but the opposite charge. Okay. So when we were doing these experiments in the particle colliders, we also revealed the existence of antimatter. Okay, so they act the same way as their other particles, but the complete opposite charge. Okay. So whereas the matter might get attracted up to a positive plate, antimatter would get attracted down to a negative plate, something like that. Okay, so an antiproton is the same mass as a proton, but a negative charge. And every particle of matter has a corresponding antiparticle. And these were first proposed by Paul Dirac in 1928, when he noticed there were 2 solutions to the equations he was developing to describe electron interactions. So beta particles. Okay. So all you need to know about antimatter is that they're exactly the same as matter, but the opposite charge. So they'll get attracted to the opposite charge. Okay. Second solution to the equations that Dirac proposed was positive rather than negative. Okay, and he named positron, which was the positive of the electron. And experimental proof of its existence came in 1932, when they were discovered to be produced naturally from cosmic rays. And this is the only antiparticle with a special name. So positron is a positive electron. The others are just anti-whatever. So anti-up, anti-down. Okay. And when you have matter and antimatter, if they collide, they can produce a lot of energy. Okay. There is actually, at the moment, evidence of a lot less antimatter than there is matter in the universe, and no one's really sure why, which I think is quite interesting. Some people even propose that there's like an anti-galaxy somewhere, or an anti-universe somewhere that's the same as this galaxy, but anti. Don't know, but yeah, I think that's quite an interesting tidbit. Annihilation occurs when a particle meets its antiparticle and both particles disappear and they produce energy. Okay, at low energies, this results in the production of a pair of photons, i.e. the combined mass energy of the particles disappears and is replaced by pure energy. Conservation of energy and momentum means that it's always at least a pair of photons, that is produced. Remember, photons is light particles. At higher energies, more than 2 photons and various other heavy particles may be produced. Many of the new particles discovered in the 20th century were identified from deliberate annihilation. So in particle accelerators, firing antimatter, let's see what happens. Okay, and the top quark was one such particle that was discovered that way, which was discovered in 1992. So we're getting closer and closer to sort of current time. And antimatter is also created naturally in radioactive beta decay, which is what we're going to talk about now. So we're almost done with all the wordy parts, sort of history parts. The neutrino and the antineutrino. We've touched on this a little bit when we talked about nuclear physics. So we know that radioactive beta decay produces an electron, okay? But how can a nucleus emit an electron when there are no electrons in a nucleus? So in beta decay, a neutron changes into a proton and an electron. Okay. So the electron is forced out at high speeds due to the nuclear forces, and it's carried away, and it carries away kinetic energy, so it's moving quite quickly. Precise measurement of this energy that the electron moves off at shows that it's not just distinct energies that it moves off at, which we would normally expect, because we know that if you know how much energy something's got, you can work out how much kinetic energy it's got. But when they did the experiments, they realized that wasn't the case. We couldn't predict exactly what kinetic energy it would have. There's a range of energies, okay? If you did it with alpha particle, you would get this energy, that energy, depending on the mass, okay? But with electrons, from beta decay, we got this range of energy, okay? And that's what confused people a little bit. It's like, how can we have a range of energy if we know what energy it went in with? We should be able to work it out. So, for example, protactinium emits alpha particles with 9 distinct energies. These separate energies can be calculated from the difference in the energy of the emitting nucleus before and after the decay process, E equals mc squared. The electrons in beta decay come out with a range of energies up to, but not including the expected value. Something was needed to account for the missing energy and momentum, and that was your antineutrino. Now there's a bit of writing here because the notes are a little bit wrong. Okay, so in beta minus decay, I've put an example here. This is beta minus decay because this one here is beta positive decay. It's a little bit confusing with the notes. So that's why I put a line in here. Okay, so Pauli proposed in 1931 that there must be the second particle emitted in the decay to account for all that energy. Since this has not been detected, it would have to be neutral and highly penetrating so it can get really far, meaning it did not interact with detectors. It was later named as a neutrino, but we now know it's an antineutrino. So in beta minus decay, which is the one that you need to know, we've got a proton, we've got a neutron changing into a proton plus an electron, plus this extra energy which comes in the antineutrino. So if you were to write beta decay, again you'd increase the number of protons, but the mass number would stay the same, give out an electron and also an antineutrino. The one underneath, which was a little bit wrong, is your beta positive decay, which you don't really need to know about, but it's just kind of good to have a whole picture of what's happening. It has a certain symmetry with beta minus decay, okay? So in this process, instead of a neutron changing into a proton and an electron, a proton changes into a neutron and an anti-electron and an anti-neutrino, so a neutrino, okay? So that's your beta positive decay. So you've got one of these protons changes into a neutron, okay? So we have one less proton, but the mass number stays the same because you just have one changing into another. Plus a positive electron, plus get rid of that bar, that's just a neutrino. The The little line on top of it. Okay. And more than 50 trillion solar neutrinos pass through an average human body every day. Yeah. Yeah.
So a neutron in the beta minus decay, a neutron changes into a proton and an electron. So in a beta positive decay, a proton changes into a neutron and a positive electron, an anti-electron. So is that gives N plus? Yeah, it's plus then. Okay. Or is it neutron? So it's just like this one, but instead of an A, it's an anti-electron. Okay. So and a neutrino rather than that.
And originally, Pauli suggested the neutrino is called a neutron because he didn't know about neutrons. But yeah, so that's basically that's getting rid of what was there originally. It shouldn't be a line on here. That's why I should do that. It's just a mistake in the notes. Okay. Right, and finally we get to the actual standard model, which is what this whole booklet is about. So I'll leave that up for a little bit longer while I answer a couple of questions that come from people at home. Yes. Yeah. Nothing apart from the charge. So it's the opposite charge. Like if it's positive, it'd be negative. So if one's positive, the other one would be negative. So a neutrino.
So an anti-electron is a positive electron. So a neutrino, okay, they don't have charges, they're zero charge, so some zero charge. But if they had a charge, they'd be positive. Yeah, obviously, yeah, they're all zero charge. What is that's an antineutrino. It's just near an atom with beta particles, so it's just energy. It's like an energy particle. Yes. So it's changed into your electron and proton. It's produced a new electron. What's the positive electron?
Positrons are just a special name for an anti-electron. Antiproton would be a positive proton. Oh, sorry, negative proton. No. There's no name for anything other than positron. They're all just anti whatever. Right, okay. So we're going to look now at the actual standard model. Okay? And this is like the periodic table of quarks and leptons. Okay? So standard model is currently our best understanding of the fundamental nature of matter. Okay, so there are 12 fundamental particles and they're organized in 3 generations. So they consist of quarks and leptons. Okay, now quarks, we've got up, down, charge, strange, top, and bottom. And you can see, you don't need to memorize these, but they all have different charges. So that's 2/3, that's minus a third. And they have spins, you don't need to worry about spins. Okay? And the quarks are what make up the things that we know. So we know that protons are made up of quarks. we know that neutrons are made up of quarks. The leptons are things that go along with quarks. Okay, so they're quite often like just energy or particles of energy. Okay, so the leptons are neutrino, the electron neutrino, which is given out in B today, and the electron, the muon neutrino, and the muon, and the tau neutrino, and the tau. Generation 1 is what makes up everything that we know about already. Okay, so protons and neutrons made up of and down quarks in various combinations, and also they come along with electrons and electron neutrinos. Okay, so when we've been talking about antineutrinos and neutrinos, we've actually been technically talking about electron neutrinos because they come along when an electron's made, a neutrino is given off as well. Okay, so a lot of new words now. Okay, so quarks and leptons are fundamental particles. 6 quarks, 6 leptons. They are all fermions. So fermions are fundamental particles. So fermions are the matter particles, and they consist of quarks, so 6 types of quarks, and leptons. And the first generation includes the electron, the neutrino, and 2 quarks that make up protons and neutrons. And just to make things a little bit more complicated, anything that's made up of quarks can also be called a fermion. So a proton is made up of quarks, so a proton can also be a fermion. Okay, so just a lot of new words here. So proton is made up of 2 ups and a down. A neutron is made of 2 downs and an up. Okay, and I've written hadrons there because we're going to talk about what a hadron is in a second. Okay. So generation 1, that first column, is what we're going to be coming across most often. Okay, there are generation 2 and 3 are only found in high energy collisions in particle accelerators. Okay, so most of the stuff that we know about protons, neutrons are made up of everything in generation 1. Okay, hadrons are things that are made up of quarks. So a proton and a neutron, they're both hadrons. And so the electric charge of a hadron isn't always an integer number, so a full number. Okay, so what you do is you add up the charges of the ups and downs, or the quarks that make up something bigger, and they come to an integer number, and that's the charge of the particle. So hadrons can then be subdivided into baryons, which include protons, neutrons, and particles heavier than these, and mesons, which are generally lighter than protons. Okay, so the difference between baryons and mesons are a baryon is made of 3 quarks. So a proton is made of 2 ups and a down. It's made of 3 quarks. It's a baryon. Meson is made of a quark and an antiquark. Okay, so it might be made up from an up and an anti-up, or an up and an anti-down. Okay, so those are the definitions of baryons and mesons. Okay, and particle recipes are what particles are made up of. Okay, so the charge on each hadron is equal to the sum of the charges of its constituent quarks. So, for example, a proton, 2 ups and a down. An up is 2/3. So if you add 2/3 to 2/3, and then a minus a third, you get overall charge of +1, which is what proton charge is. We know that. With a neutron, we've got an up and 2 downs. So we've got 2/3, minus a third, minus a third. So I've got 2/3 plus minus a third plus minus a third, and that comes to 0, which is the overall charge on a neutron. We know that's true as well. Okay. So an example there, a negative pion has a charge of -1, and the quark structure of this meson, because it's got an anti-quark and a quark. So a negative pion is made up of an anti-up, that line is anti, and a down particle. So up 2/3. So but an anti-up is the opposite charge to that, so it's going to be -2/3, minus a third, which comes to -1, and that's the overall charge of a negative pion. Okay. We never observe quarks in isolation, only in doubles or triples that give integer charge. We never observe changes that are fractions of the electron charge. This means that not every combination of quarks and antiquarks is possible. Okay, and the bar means antiquarks. Right.